All right, so welcome everybody. Welcome to the Scaling ML platform Responsibly with Machine Learning Observability at DoorDash. And thank you for attending this session. Cornell and I are the presenter of this particular one. But first, we would like to introduce ourselves. So my name is Heen Liu, and I'm leading machine learning platform team at DoorDash. I've been here about a year and a half. And before that, I was at LinkedIn, and as well, I spent a little time at Uber. And now Cornell will introduce himself.
Hi, everyone. My name is Cornell. I'm a software engineer on the machine learning platform team at DoorDash. Previously, I worked as a software engineer at Quora's machine learning platform team.
Okay, so in this session, first, I will provide a quick overview about DoorDash, and then share a few interesting machine learning use cases in the context of the food order lifecycle. And after that, Cornell will present our approach to ML observability. And finally, he will end the presentation with a few lessons learned and future work. So at DoorDash, our mission is to grow and empower local economies. And we do that through a set of product offering. So the DoorDash marketplace consists of many different products offerings. This is just a subset that you see on this slide. The first one is about food delivery and pickup. So this is where customers like you and me can order food on demand for like breakfast, lunch, or dinner and such. The second product is about convenience and grocery. And this is where customers can order everything from non-food related items, such as like sunscreen, or to entire weeks of groceries. And the last one is called Dash Pass, which is a subscription product that is very similar to the Amazon Prime product. Now, you probably can guess or have heard that DoorDash is a three-sided marketplace. And like most marketplaces, it has this flywheel effect, meaning that the more activities there are on the marketplace, the greater the value it will bring to other parties on the marketplace. In our case, we have consumers, dashers, and merchants. Now let's go into some of the machine learning use cases on our marketplace. And I will do this in the context of the food order lifecycle that you might be familiar with. So it consists of the following steps: creating order, right? Order checkout, dispatching order, and delivering order. So the first one is creating order. This is when our customers land on a DoorDash homepage. And then we want to surface the most compelling options to them. And this is where our recommendation models play a big role in that regard. And then if customers don't see anything they would like for that particular day or in the morning, then they can go and search for what they would like. And this is where we leverage a set of search ranking models to help with providing relevant search results. Once the food items have been added to the shopping cart, the next step is the order checkout. At the top, you see are the ETAs, which means estimated arrival times, which are really important for setting customer expectations on when their food is going to arrive. If we quote too conservative, the customers might not order those, or too optimistic, then the order might be late and customers will not be happy. So it is very important to have as accurate as possible about these ETAs. And we predict these ETAs based on a number of factors, including the size of a shopping cart, the historical store operations, the number of dashers available at that particular point in time. And then at the bottom, like most internet e-commerce companies, we need to combat fraud. So on the payment section, we use a series of fraud detection models to identify fraudulent transactions. So once the order has been paid, then the next step is to dispatch the order. And this is where our logistic engine takes over, right? It figures out which dasher to send the order to and how to send to the merchants. And in order to do this, it relies on several machine learning models, such as like predicting how long the food preparation time is. And then also predicting the travel time, how long does it take for the dasher to go to the merchants to pick up the order. For this, it has a few interesting nuances, such as traffic, weather, what we don't have much control of, right? Another interesting challenge is, unlike Amazon orders, food orders emerge on the fly, and the food quality plays a very important role in the delivery itself. So that has to be taken into consideration when assigning orders to dashers. Finally, the last step is for dashers to deliver the food to the customer's doorstep. During the pandemic, we introduced the contactless delivery, um, and that creates a few interesting challenges. One of them being that customers often had a difficult time finding their orders, so they would report their order has never delivered. So that's not a good experience. So we asked dashers to drop the food off near the front door, and then take a photo of the food and then send that to the customers. And on our side, we use deep learning models to identify whether the drop-off photo has a door or not, because having a door in the photo is a strong indicator that it was actually delivered to the doorstep. So now we're going to go into talk a little bit about the machine learning platform journey. These are the pillars of our platform, and you can see that they are modeled after the machine learning development process. And the approach we use in building these pillars starts with thinking big, or think big, by working backwards from the customer's needs, all right, and put together a product vision and a strategy around it. And then we incrementally build these pillars out based on the needs of the community, while keeping an eye out for the long-term vision. And once we have onboarded more complex use cases on our platform, then interesting scaling challenges emerge, which is expected. And I'll share a little more details about that. Now, in terms of our prediction service, we follow a principled approach in building it, meaning start with a strong foundation that works and scale it out as needed. So we build a centralized prediction service that is easy to manage, monitor, and operate. And with this strong foundation and a few unique features, we were able to support up to about 15,000 peak predictions per second. And then we took on a important and very high visible use case called search and ranking, which has a much higher QPS and low latency requirements than the other ones. So our initial approach is to scale our prediction service horizontally to support such requirement. And then the next big one comes in, which is another highly visible use case, which is called personalized recommendations. It has much higher QPS and low latency requirements than the previous one. And how it works is, every time a customer visits DoorDash homepage, the recommendation candidates are fetched and ranked. So therefore, it often needs to perform like thousands of predictions at a time. So scaling out is not an option anymore. So what do we do in this case? So we went to the drawing board to really figure out where the bottlenecks might be, and then identifying the necessary optimizations in order to scale our prediction service. We ended up optimizing our prediction service. There's some optimization at the low level, the gRPC level, the protocol level. And then we redesigned the way we store billions of features in our feature store to improve efficiencies, reduce latency, and costs. We also sharded our prediction service to give us more flexibilities in terms of scaling them vertically or horizontally when needed. So with these optimizations, our prediction service was able to support up to about 6 million peak predictions per second. And then we were able to onboard the personalized recommendation use case successfully. Now, with these important use cases onboarded, then the ML observability has become a really important area to pay attention to. And now Cornell will share more details about this topic.
Thank you. Next up, I'm going to be talking about the story of machine learning observability at DoorDash. So I want to share the story of how DoorDash integrated monitoring to its machine learning platform. Once we integrated our ML systems with our product, we saw a need for monitoring. Data scientists wanted to know what decisions we are making and why. We then consulted with our data scientists to understand what would be the most helpful for them. Based on that feedback, we quickly implemented a first version of monitoring using MLOps principles. We immediately saw the benefits of monitoring, so we ended up iterating on it more to get more out of it. I'm sorry, I think I hear some echo. Do you mind maybe muting yourself, Ian? Maybe that helps. Yeah, I'm not sure. Yep. Thank you. So as Ian mentioned, ML gives us a reliable signal for the time it takes a restaurant to prepare food order or how long it will take for an order to reach a customer. However, once an ML model is deployed to production, it immediately begins degrading, and this degradation negatively impacts the accuracy of our time estimates. And model predictions tend to deviate from the expected distribution over time. For example, a shift could be a result of an external event, such as the COVID-19 pandemic, which caused a huge shift in how customers interacted with DoorDash. Using observability and monitoring, we want to protect the downside and avoid bad outcomes. In a few cases where we went through a migration to a new feature upload system and experienced some issues in our downstream model prediction. Had we had monitoring, we would have been able to detect these shifts sooner and fix our models. So what should be monitored in an ML system? Because ML models are derived from data patterns, their inputs and outputs need to be closely monitored in order to diagnose and prevent model drift. We believe that monitoring and testing should be present every step of the way. What we are focusing on these major steps: the data quality, model training, prediction, general system performance, and then additionally, our users like to also understand why their models made specific predictions, which we refer to as ad hoc inquiries. In this table, we laid out the high-level areas and two additional dimensions: observability and explainability. For the data quality, we are investing into a data quality service, which includes adding safeguards to data inputs before they reach the training phase. For the training, prediction, and system areas, we develop some tools in-house and also use industry standard tools such as Shapely plots. Finally, we power ad hoc inquiries by providing dashboards and notebooks, as well as our one-stop machine learning portal where people can have an overview of their ML application. I will cover model training, model prediction, and system performance in more detail. First one is model training. During model training, we want to make sure that the inputs that we feed into the model are as expected. We verify that there are not excessive amounts of missing values and the distribution of features is as expected. We also focus on tracking. We heavily rely on open source tools such as MLflow to keep track of model training runs. For feature importance, data scientists like to look at various properties of features such as the distribution values, negative percentages, and missing value percentages. So here's an example of a data quality breakdown that they like to look at. Another standard way of looking at things, like the effect of features on the output, is a game theoretic approach called Shapley. So we create a large number of these Shapley plots to understand what is the effect of the features on the final predicted value. Finally, we also look at other standard plots such as feature importances. The next area I'll cover is model prediction. In our production environment, when we receive a prediction, we log it along with the features and the predicted value to Snowflake. So our main approach here is then to construct queries against these tables to derive statistics such as average or percentiles. For the most part, we consider numerical values, but it could be extended to different types as well. In the case of production feature monitoring, similarly to training time, we perform certain checks on features. We collect descriptive statistics and we pay special attention to the number of default values or zero values. As you can see on these graphs, we keep track of these values over time. We also want to monitor the outputs of ML models, the predictions. We monitor descriptive statistics similar to feature monitoring. For example, we predict the expected time it takes to deliver an order, and we want to monitor those predicted values over time. We want to make sure there are no unexpected outliers in order to continuously provide a great user experience for DoorDash customers. While understanding descriptive statistical properties of our predictions is valuable, a more useful metric would be to, for example, to tell us how close our predicted values are to the true values. In the case of delivery estimate, we can infer the actual delivery time by the difference between when the delivery was placed and when it was finally delivered. There are a few key challenges with determining which evaluation metrics to use or how to refine them for our monitoring system. In some applications, such as the prep time modeling, the data is censored. That means some measurements might not be available to us immediately. In other applications, such as predicting fraudulent orders, the true value might not become available for weeks because the payment processors and banks need time to process those orders. One commonality between these two cases is that the predicted and true values need to be stored separately. True values are often available either explicitly or implicitly in our databases for a given prediction ID. Once we make the connection between the prediction ID and the database row with the true value, we can build a joint query and use a commonly available evaluation metrics. So some computations can be done using elementary operations, but for more complex metrics, we can use Spark jobs in a distributed manner. Machine learning tasks can be categorized based on what type of prediction they make. For example, for regression, we can use mean squared error, and for classification, we can use precision and recall. So here's an example of a mean absolute error evaluation metric over a period of a month for one of our most important models, the prep time model. So you can see that there are various anomalies that can be picked up, such as the error rate spiking at one point. Another important aspect of monitoring is the system health and performance. We follow standard service reliability best practices and monitor requests and prediction counts, availability, and latency. We have tight alerting on each of these components since other systems such as delivery, ET, and fraud rely on prediction, and the changes in quality can have significant impact on those. One key advantage we had is the presence of good infrastructure foundational building blocks at DoorDash. We were able to leverage our internal Terraform repository for alerting, where we can basically create queries using PromQL. We can add thresholds and connect alerts to either a team-specific Slack channel or a team-specific PagerDuty application. Our observability team already used this infrastructure within the company, so this was now a new tool for our data scientists and engineers to learn. We also were able to take advantage of standard tools in the industry such as Kafka and MLflow. Along the way, we saw 5 key benefits of developing our machine learning production system. The first one is leveraging existing tools. We can design a configurable and flexible platform for displaying metrics and setting up alerts by reusing tools. The second is no onboarding is required, which means that data scientists don't need to individually write code and add monitoring to their training pipeline. They also do not have to think about scalability and reliability of their monitoring solution. Thirdly, open source standards. By using standard open source observability tools such as Prometheus and Grafana, data scientists and engineers do not need to learn a homegrown system. Easy visualization. So graphing tools such as Grafana offer the ability to interactively view splits and historical data. This is an incredibly useful tool when it comes to finding correlations between events. Self-service. So data scientists can use this tool without the help of the ML platform team. which ensures more scalable detection of model drift going forward. Next up, I will talk about how our platform evolved and what results we saw. With this first release, we had a fully functional monitoring, graphing, and alerting workflow for detecting model drift. Thanks to close consulting and coordination with data scientists, we were able to onboard many teams for the first release. Based on their usage and feedback, we made several improvements. In our first release, we enabled monitoring flexibility for data scientists by allowing them to configure the specific metrics they wanted for specific feature names. This had the drawback of requiring an onboarding step for new models and feature names. In our second release, we enabled complete monitoring for all models, feature names, and metrics. This achieved our vision of out-of-the-box experience. Initially, we calculated statistics at both the hourly and daily aggregation level. It turns out that the hourly is far more valuable than daily, since we see peaks around lunch and dinner times. In our second release, we focused on hourly aggregation, rebuilding the monitoring system using our real-time processing pipeline for real-time graphs and alerting using Kafka. Another improvement to the output monitoring came with the introduction of opt-in evaluation metrics and connecting predicted values to true values, which is a prep time model I showed earlier. So the launch of monitoring enabled us to actively monitor the performance of ML models, which was especially useful for internal teams at DoorDash, such as logistics and fraud. And providing model monitoring as an out-of-the-box experience was well received by the internal data scientist community at DoorDash. Feedback after our launch was immensely positive and made it clear that we helped our data science customers improve their model performance. As an example of a success story, we applied our monitoring systems to the fraud ML models, and at some point we noticed a sudden change in the distribution of predicted values. So this kicked off a investigation into the feature extraction code and prevented some potential larger scale issues, and therefore proving the usefulness of the monitoring platform. To wrap up, I'll cover lessons learned and future work for the entirety of today's presentation. First, scaling out doesn't always work. Sometimes you have to think outside the box and get back to the drawing board. And then providing out-of-the-box solution is preferable in most cases. Automation is key for any large-scale system. If you have a good foundational tools, you should probably use them. We've also learned that using existing tools can be very beneficial. And finally, working closely with customers is necessary for a good outcome. So always seek feedback as well. Looking forward, we want to make incremental improvements to the monitoring system. First, we want to make model prediction optimizations as well. So as the prediction request volume increases, and we expect that this will happen in the near future, we are looking into the potential of caching the feature values as well as prediction results. And there will be many interesting technical challenges in these areas. Secondly, descriptive statistics and alert thresholds are a powerful tool for catching issues. However, a metric might not experience a sharp change, but rather a gradual change over time as a result of changing behavior and long-term effects. A general area of research that we could tap into is anomaly detection, where we can treat predictions as time series data and detect outliers that happen over time. Finally, model explainability. Oftentimes, ML models can produce unexpected results that can be difficult to interpret, delaying investigations. This is an especially common problem with more complex models such as neural networks. To mitigate this problem, we want to double down on our investment into model explainability. In addition to the generally available tools that I mentioned earlier, we want to develop additional tools to best serve our data scientists. Thank you for your attention. If you'd like to learn more about machine learning at DoorDash, I'd point you to our engineering blog. We are also growing quickly and hiring, so if you're interested, please head on over to the careers page, and there's some links on this page as well. Lastly, we also publish these findings in our blog titled Maintaining Machine Learning Model Accuracy Through Monitoring. And thank you for your attention.
Thank you, Hien and Cornell. Really appreciate it. We have time for just one, maybe two questions tops before we take our break. The first question actually came from Oren. He asked, is explainability important for you and, for example, in recommendations?
Yeah, that's a great question. Thanks. So explainability is very important because oftentimes a model can be very complex, and we see a incorrect prediction or like incorrect recommendation in our homepage feed. And in order to really understand why that happened, we have to understand why the model made the prediction, why we then did filtering. There's also like there's a first phase where we select stores that are candidates that we even show. So there's many different layers, and the complexity increases over time as we develop our system. So it's important to insert model explainability at every level in order to continuously improve our recommendations.
Awesome, thank you. I think maybe time for just one more question, and I'm also going to ask Oren if you can unshare your slides. We can get ready for our break. The final question is, could you please explain how model monitoring, especially predictive drift, help you identify root cause?
Yeah, so basically we used the graphing tools available to sort of like do a correlation analysis where we see a shift in the predicted values and the true values and the statistical metrics that we look at over time. And those have helped us in the past understand like drift. Drift is a difficult thing to detect because it can happen slowly. So if you look at it week over week, you might not get any signal. But we also compare like for many weeks going back, and we have been able to detect differences that way.
Awesome, thank you. Well, I think we'll wrap up at this point. So thank you again, Hien, Cornell, for a great presentation. You can head off to the backstage, and we're going to go and take our break now.